very similar to how we looked at the product rule. And we said, we saw some functions that were expressed as a product, but we learned in some of our early derivative rules that if we can rewrite them, that sometimes that was easier than trying to take the derivative of a product. And I want to kind of apply the same approach here to the quotient rule to see a function that's a quotient where maybe we don't have to use a specific quotient rule, and then let's introduce a function where we do. So let's consider the function f of x is equal to, and it's going to be a quotient here, it's going to be 4x squared minus 2x plus 3, and that is all over x. Well, one of the things we said when we learned our early derivative rules is that if there's a single term in the denominator, I can split this up as 4x squared over x and 2x over x and 3 over x. In fact, I can split up a numerator of a fraction. What I can't do is split up a denominator. But because there's a single term here, to find f prime of x, what we did was we rewrote, so we can rewrite f of x. And what we wanted to do here is we wanted to take f of x and do exactly what I said. We can say 4x squared over x minus 2x over x plus 3 over x. And if I go in and just kind of simplify this so that now I can take the derivative, this works very nicely because if I have that single x in the denominator, I can do some reducing, some rewriting in a way that's going to get it in that polynomial form that I can take the derivative of. So 4x squared over x is going to divide off an x, and I'm going to be left with 4x. 2x over x is just simply going to be minus 2. And then 3 over x, I know because we're going to take its derivative, let's go ahead and rewrite that as 3x to the minus 1. And now I can take the derivative of this pretty easily. I can say f prime of x is equal to, well, the derivative of 4x is 4. The derivative of minus 2 is 0. And the derivative of this, if I take the negative 1 times 3, that's minus 3 x to the minus 2. And so if I go rewrite it without negative exponents, I get 4 minus 3 over x squared. And you may see this written a couple of different ways. One way of simplifying it, you might see somebody find a common denominator here and write this as one term. You could actually write this 4 as 4x squared over x squared. And so you would also get an equivalent form of 4x squared minus 3 all over x squared. These are equivalent answers, and either one of them is acceptable for right now if it asks you to find the derivative. And so one of the things you're going to see, particularly with quotients, is it's going to be very possible to get equivalent answers that may be expressed differently. These two things right here are equivalent, they just look different. Well, let's take a look at a function. In fact, a function that we addressed at the end of topic 2.6. At the end of topic 2.6, where we learned all of the rules that let us go from here to here. We finished topic 2.6 with the function g of x equal to 3x squared plus 7x minus 4, and that was all over 4x plus 8. And the thing that was different was that now the denominator was a binomial. So if I try to split it up, I would get 3x squared over 4x plus 8, but I can't split up the 4x plus 8. That's one of the rules you learn early on when it comes to operations with fractions, is you cannot split up the denominator the way you can the numerator. So because we cannot rewrite this function g of x as a polynomial the way we could this function f of x, and so because we can't rewrite it, then now we have this need. We need a special rule for quotients called the quotient rule. So as you're going to see in this lesson, just like we saw with the product rule, if you can rewrite a function, that's a pretty easy derivative to take in terms of what we're going to get into in this class. But there are going to be times where you cannot do the polynomial rewrite, and that's where we'll need the quotient rule that we'll learn next.